Like I said, my name is Jason Lawley. I'm excited to be here. If this were baseball season, I would actually be a pinch hitter because I was not originally scheduled to be here. But because I live just down the road in near Boulder, they said, well, we need a speaker. Can you do it on a Saturday? And I said, sure. I'd be excited to come and do that. So I am a data center solution architect is my current role at Xilinx. Essentially what that means is I help all of our customers with their architectural needs, all the way from helping them define their architectures to going through and implementing them in the Xilinx solution. And what we want to talk about today is how we're seeing this move to real-time AI and what that needs. We have Siri and Alexa. We've given them names, right, when we talk to them on our phone. The response times need to be very quick for that. We have home security systems now with Ring and a variety of other ones where those videos are going up and being able to near real time determine if there's an intruder or there's something wrong at our locations. And then commercial services. I don't know if you've been into a Target or a Walmart lately and you look up on the ceiling and it looks like you're in a casino now, right? Because they've got so many cameras or so many camera bubbles that are up there where they're looking to monitor what's going on in their stores, whether it's for theft, whether it's for keeping track of employees. So there's a lot of real-time AI inferencing that needs to happen. So from a Xilinx point of view, the way we look at things, the way we look at the world, is we've got CPUs on here on your left-hand side, right? And this is where the vast majority of AI inferencing workloads are done right now, I think, right? I mean, I think there's a move towards trying to use GPUs and FPGAs, but CPUs for a lot of applications that are not necessarily real-time work just fine. And then you get into domain-specific accelerators, which again are the GPU-type accelerators. And then you get into what the Xilinx acceleration platform looks like, and we call this adaptive compute, right? So since I haven't presented here before, and I don't really know many of you, how many here have used Xilinx before? Can I get a show of hands? Okay, a couple. Good. How many here have used a GPU before? All right, many more. Okay, that's good. So the way that I think about the difference between a GPU and an FPGA or an adaptive FPGA is that when you're running a GPU, you have a fixed set of resources that you can use. When you go and code, right, you're coding in like a C or a higher level language, and you're giving that GPU instructions. With adaptive platforms, you are literally building a physical structure that is going to implement the computation that you need to have done, right? And if you think about that, that's pretty amazing to be able to build a physical structure that can run so much faster than what you would be able to do in something that's fixed. So we have this adaptive platform, and so what we have is you can still buy from us a number of chips, right? So you buy a chip off the shelf, you can develop your own card, and you can create that design, put your design out there. If it needs to be updated, you can do that, right? You can update the actual physical structures that are there. But we also have introduced our Alveo line of cards. So this line of cards is a different devices, but the cards themselves have been qualified for production. So when you're ready to actually take those designs and implement them and push them out into the wider world, the cards are ready to go. So it can definitely save time from being able to get your initial designs up and running to full deployment. And as Ganesh said, there's a U50 back here, which is our latest one that we just announced. It is a half-height, half-length card, so it's much smaller than a form factor than you see in a typical GPU. And it does have a QSFP25 port on it, so you can do network acceleration, you can do compute acceleration, and it also comes with 8 gigabytes of HBM memory, right? So being able to get into that memory there's 32 different AXI media ports that you can go and access that 8 gigabytes of memory. So it's a pretty incredible amount of power in a small little package. So once you do have that hardware, the next thing that comes to mind is, well, how do I actually create this design to put in? And that is always the sort of the hard part, I think, for Xilinx to a certain extent. So I consider Xilinx, we are a hardware company trying to transform into a platform company. And Vitis is a new unified software platform that we just recently announced in October. And what we have is we have our cards that you see on the bottom. So we have our hardware platform that you build on. On top of that is the Vitis target platform. So this is a way to think of, we call it a shell sometimes, we call it a platform, but it is essentially a bunch of things that you need to access the cards, whether it's PCI Express, whether it's you want to access the temperature of the card. All of that's already been done for you. Because as I said, the devices, when you get them, they really are a blank canvas. So if you're an artist and you're looking to do something with Xilinx, it's a blank canvas that you get. What we try to do with this platform is give you sort of a starting point. So maybe we've given you a sky and a landscape for you to put the rest of your important stuff on. Then we have on top of that, let's see if my pointer's working. No, I don't think it is. Okay, but we have on top of that the Xilinx runtime libraries, which is the host side. So when you have your host is actually running, where you have your CPU, this is a way to create a program that will now interface to that card that's plugged in. And then on top of that, I think this is probably the most important part for a lot of people, is up these top layers, we have introduced a number of different libraries that are available. So in order to get you up and running as quick as possible, we have OpenCV libraries, we have finance libraries, we have math libraries, we have TensorFlow. So we're adding support for a lot of these different platforms to be able to go and easily implement. So now that I've given you sort of a baseline of what Xilinx is about, so this is, and I'm going to tell you a little story here that goes along with this. So there's a lot of different use cases where we want to do important things, where we're looking at information that we need to classify very quickly. And so last week, my 15-year-old daughter is a water polo player. We happen to have a water polo tournament here in Colorado. And in the morning, it was like a Sunday morning, I got a call from our person that we work with who's in South Korea, and he said, well, the server in Longmont is down. Can you go up and put that server back online? So I said, sure, I've got this water polo tournament, but my daughter's got a big break. I'll just take her. We'll go up into Longmont. We'll get that server set up. So we go and drive up to Longmont. We have lunch, get into Longmont, and we go and get the server back online. And she goes, well, I have to go to the bathroom before we leave real quick. I said, okay. So she goes in the bathroom. I'm sitting there. It's like 5 minutes go by. And I'm like, what the heck is she doing? And she comes back out, and she's like, oh, that's a very nice bathroom. Which I thought was really funny, right? And I sort of now, if you've ever watched The Office, I sort of think that maybe our bathroom in Xilinx is very nice on the women's side, but not on the men's side. But I've not been inside myself to know. But I said, yeah, I mean, it's a corporate bathroom. And I was like, well, what took you so long? And she's like, I was making a TikTok. And so, is anybody here familiar with TikTok? Did I see a few people? Okay, yeah. This is a video, right? So, the conclusion that I reached, the reason that AI is so important in what we're doing, is there's a lot of junk out there that we have to filter out, right? So what a 15-year-old is doing in making a TikTok in a corporate bathroom for her friends to see, I'm sure there's very little interest in the advertising community of that. But I think that, you know, there's important stuff that we need to get to, but there's a lot of junk out there that we want to get past. So one of the things that we see with the Power AI vision from IBM is the ability to make it so that we can take maybe experts in their field and make it easy for them to create and deploy machine learning solutions. So typically what we have to have happen when we're doing a flow like this is we have our label or image or our video data, and we go through and we get different images that we need to, that we want to classify. We create a data set, we prepare that data, then we actually train our model. Once we train our model, we need a way to deploy that. And that deployment, it could be to a data center, right, where you'd see an Alveo card. It could be into a car, it could be into a drone, it could be into a number of different places. And so what we have with this Vitis AI integration is we do have this flow where we can create the data set, we train the model, we go through Vitis AI to put that out. The model gets quantized down to a level where it makes sense, where we get the performance that we want from that model, both in terms of its accuracy and its how fast it's able to accelerate things, how many images is it able to sort, and then we can deploy that into the system. So, again, taking this one step further, and I should tell you, I have no idea how long this presentation is going to be. I have half an hour, right? And I might be way ahead, so I apologize in advance if I'm going too fast. So now it's much easier if you think of it from a user point of view. They come in, they train their system. In the middle here, they can now deploy their system, and then they have an API where they can access the different functions that they want once that system has been deployed, hopefully on a Xilinx device, but I think it's fairly easy to deploy it on other devices. So that was sort of the main thing that we wanted to show you, is just that there are ways now that are coming to make it much easier for non-technical experts to actually go and train and deploy AI systems into the cloud. And I have a video here that I'm going to run through here at the end, and it will show you sort of what that flow looks like when you're going through and doing the classifications. And I'll go ahead and play that, and while I play that, I'll go ahead and ask if there's anybody that has any questions. I'd be happy to try to answer them. They can be related to this or really anything around Xilinx and FPGAs and adaptive compute. So, no questions? Okay. Anybody make any TikToks? Yeah.
Not a TikTok.
Okay.
What industries do you see deployment of Xilinx most prevalent?
So in terms of like the industries where we see Xilinx being deployed, I think one of the hard things for Xilinx, as I said, we're sort of coming of age, I think a little bit, is that the number of industries is really, really quite broad for where FPGAs get developed or get deployed into. I think the main ones though that we see typically are communications, right? Anything that's like data center, networking, those types of applications make a lot of sense. We get deployed into base stations of cell phones, right? So anything that's very low latency that requires lots of compute but low latency, FPGAs are very good at. So, and that's why we see, when we talked about at the beginning, things like speech recognition and being able to, how quickly when you ask for something from your smart device, do you get a response? We see FPGAs starting to creep into that area. Same with video and like automotive. It's something where that low latency is really extremely important. So.
Can you say something more about the programming support, whatever you want to say?
Sure.
About that.
Okay, yeah. So essentially, we've got two different flows actually that we're sort of now pushing. We've got the typical flow, which would be more targeted towards an RTL developer, so somebody doing Verilog and HDL. We call that Movado, right? So that flow is a flow that's going to exist. It's used by a lot of our customers. The new Vitis flow is really targeted more towards C or C++ type users. Now, when you write your C or C++, it's important to keep in mind that you're still creating a physical structure inside of the FPGA. But in addition to that, with this Vitis flow, because we now have given you libraries that you can put into the FPGA device, it makes it so you can get that much faster in terms of defining, especially like if you're doing compression or something that's in a library that's used over and over again, makes it much easier for you to do that development. So what you end up with at the end of the day, when you do that byte flow, you run through, you'll actually get what we call an XCL bin file, which is just the firmware, the binary that goes inside of the FPGA. And then on the host side, you're going to write your host code, which is essentially taking the data that's that you have either in storage or you have in memory. You push it down into the kernel, which is the accelerated part of the FPGA. That acceleration will happen. You'll get a notice back that says that acceleration is done, the data is ready, and then you can go fetch it. So that's the mode that we're moving towards, especially for compute type applications in acceleration type.
Do you have any plan to move to connecting the systems with CXL because of PCIe?
Okay, so CXL, that's a good question. I didn't know whether we were allowed to talk about CXL or OpenCAPI.
No, you can.
We can talk about all of that? Okay.
Yeah, that's okay.
So-
IBM is part of that too.
Okay,
Yeah.
perfect, yes. So for those of you who don't know, right, so PCI Express is the typical way that you move data from the host to the accelerator and then back. And it's sort of interesting, I was actually just talking to somebody about this. When PCI Express was first born, 13 years ago, I think, is when it came out, nobody on the PCI Express committee said, you know what, this PCI Express is going to be great for machine learning, right? That was not what they were thinking. The machine learning was just a glint in somebody's eye. And so we've seen sort of this, we've seen sort of three different protocols that have come up to sort of try to take the place, not take the place, but extend PCI Express. So one of them is CXL, one of them is C6, and one of them is OpenCAPI. And so they all sort of do the same thing, but maybe in a slightly different way, right? So what both CXL and C6, and those are the ones I'm most familiar with, and I think OpenCAPI is similar, is what you try to do with those is you put a cache on the accelerator. And now the host, rather than moving a big chunk of data down to the accelerator, all it does is pass down a pointer. And that cache has hopefully been populated within hardware already with that data that you're already going to be looking to pass down. So you pass down that pointer, the accelerator goes and it looks in its cache first and sees whether or not that data exists, and if it doesn't, then it goes out and it gets that data from the system and pulls it down automatically. So the question is, are we as Xilinx looking to do that? We've not made any announcements at this point. I can tell you that something that's not very well published. So Xilinx, I should back up as well. Xilinx was one of the sort of founding members of C6. We also have OpenCAPI support. And we did also join the CXL board of directors. So we are on board of directors for CXL. My guess is that we're going to go with whatever our customers demand. There seems to be a big swell about CXL right now. And so I think you'll see us eventually announce support for CXL. I think that's pretty much a foregone conclusion. I think for us the bigger question is, will we continue to have C6 support? And we might, because C6 has some it has some architectures that are only possible with C6, where CXL is really meant for the processor to be the center of the universe and sort of drive things down into the accelerator. C6 is more of a balanced implementation. And so there are some use cases where C6 makes sense. So I think you'll see us have both in the future, in the next 3 to 5 years.
Have you seen the drive towards this AI automation on the tolling industry?
A drive towards what?
The tolling industry, the toll industry.
Oh, the toll industry.
Yeah.
You know, not that I know of, and I think the reason is that it's not as important to do real time there, right? Like they're going to take a picture, like how many, like a car goes through once every second, right? And maybe you have 1,000 toll booths, and that's probably a big number. I know in Denver it's probably much less than that, right? In this area maybe you've got 300 toll booths. So the one picture you take, it's not as important that it's real time. Where we do see much more interest for, at least for our devices, is more in the high-end automotive manufacturers, where they have the different cameras. So you've got sensor fusion, where you've got so many different cameras coming in. You've got different sensors, whether it's radar or lidar coming in. You need to fuse all that data together and then get it so it can be processed in milliseconds, right? So you don't run over somebody or do something like that. That's where we see much more interest in our devices.
How about the parking lots, like, based on the latitude of the parking lots, which part is open? Are there anything like?
Not for us, I mean, our devices, the Xilinx devices are, I don't want to say expensive, but let's just say they're not cheap, right? So like most people will look, if it's something that they can do with a processor, right, with just a processor, that's going to be the thing that they choose, right? Because I think computer power is fairly inexpensive. It's when you have that combination of that you need compute power and low latency, that's where programmable logic makes a lot of sense. Perfect. All right. Well, thank you so much. I actually have to hop out of here because I got to go to a hockey game, and not for me, for my son. But it's been great talking to you. I will be at Supercompute in the Xilinx booth if you guys have a chance. I don't have a very nice giveaway in terms of like being invited to like cool places, but I might go now to the Mellanox event since I've been invited. But if you do want to come by the Xilinx booth at Supercompute, I will be there. We'll have a number of demos there, so I hope you do take a chance to stop by. So thank you very much.
Thank you.